Hello and welcome to the third installment of the series of videos for transformer and inductor practical design. Today we're going to talk about how to measure the unknown value of an inductor. This comes in useful if you have inductors in your parts box that you don't know the value of, or if you wind your own inductor and want to verify its value. So normally the way that we go about measuring the value of an inductor is with an LCR bridge. However, most LCR bridges are incredibly expensive, usually on the order of a few $1,000s. And they also measure the inductance over a wide range of frequencies, usually from DC all the way into the megahertz range. However, for most hobbyist applications, we do not require this level of precision, and therefore we don't need to spend this sort of money on an LCR bridge. So what I'm going to show you today is a method of measuring inductors relatively accurately to within 5% and using only your scope and your signal generator. So for starters, let's talk about a little bit about what we actually need to do this. As I stated before, you're going to need your scope and your signal generator, or some method of actually creating a variable frequency signal at a constant amplitude. You will need a capacitor of known value. It cannot be electrolytic. It has to be either polypropylene or ceramic disc or some other type of non-polarized capacitor. And optionally, you should have a multimeter that can measure capacitance. This is usually a pretty common feature on most multimeters, and most of you should not have trouble with this. So, a little bit about the theory behind this technique. I'm sure many of you are familiar with the basic LC circuit. This particular circuit that we're using is the parallel LC circuit. And the thing about this that is rather novel, and what allows us to actually measure the inductance of an unknown inductor, is that the impedance of this network, as to say basically the AC resistance from this point to ground, is at infinity or incredibly high open circuit when this system is or signal is applied to this system at resonance. So essentially what this allows us to do is to adjust the signal here with the signal generator and move the signal up and down in frequency until we see the maximum amplitude on the oscilloscope. Seeing a maximum amplitude of this signal, assuming this signal does not change from the scope, tells us that this network is dropping the least amount of power at that frequency, and therefore that is our resonant frequency. So, a little bit about the math. This particular equation is the frequency equation for an LC circuit, and it is normally derived by setting the capacitive reactance equation equal to the inductive reactance equation and simplifying and solving for F. That leads this equation, which states F equals reciprocal of 2 pi times the square root of L times C. Now what I have done is algebraically solve for L in this equation. Now this gives us the equation 1 over 4 times capacitance times the square of frequency times pi squared. So essentially, if we have C and we have F, we can solve for L. So let's start with C. The reason I recommended that you get a meter like this instead of just relying on the value printed on the capacitor is that most capacitors have a tolerance. In this case, for this cap, it's plus or minus 10%. Now, if we do not measure this capacitor and get an accurate value, that 10% error will actually show up in our final measurement. So, as of right now, we are going to actually check the capacitance of this cap. And it comes out to 0.47 microfarads. So that is the number that we will use in our final calculations when we get frequency. So now that we have the capacitance value, we need to find frequency. So we're going to start by connecting the inductor and the capacitor in parallel and connecting them to both the scope and the signal generator. This is easier said than done. It's a good idea to try and get the two components as close together as possible, That way you eliminate any sort of parasitics that might exist from the test leads or connecting leads between the two components. And then we will also connect the scope across this as well. There we go. So now that the two are connected, we can see that there is some signal on the scope here. So we will adjust it. Bring it down in amplitude. So now what we will do is we will slowly start changing the frequency. And as you can see, taking the frequency up actually increases the amplitude. So we will continue to increase the frequency until we reach a point of roll-off. Meaning that as you go up in frequency, you'll notice that the amplitude reaches a point where it starts growing slower and slower for each increase in frequency, and eventually start rolling off in the opposite direction. As you can see here, we continue to go up. And then as you can see here, right as we approached 14 kilohertz, it actually started to roll off in the other direction. So what we will do is we will bring it back to right around 14, and we will go one more digit in and adjust it further. And it looks like about 14.5 kilohertz is our magic number. So now that we know the frequency that this particular tank circuit resonates, and since we know the value of the capacitor, we can put these values into our equation and solve for L. Now, I'm going to assume you know how to do your basic mathematics and unit conversion. So, after putting in the value for C of 0.47 microfarads and the value for F of 14.5 kilohertz, we come out with an answer of 256 microhenries. Now, this is very, very close to the manufacturer's spec value in the datasheet of 220 microhenries. That value, just for your edification, is 1.4% off. So that's pretty good accuracy, and it comes well within the manufacturer's spec tolerance and also within the spec tolerance for most hobbyist applications. Obviously, if you're a professional engineer, you probably use an LCR bridge, but for most hobbyists, this technique is incredibly effective. On the next video, I'll talk a little bit more about inductors and how to calculate and actually check for saturation point.